more quantifiers today. So we're getting used to these new symbols. This upside down A, that means for all, and this backwards E means there exists. So if p of x is a propositional function, and we're talking about some domain of discourse, maybe x is people or numbers, okay, then this notation means for all x in the domain, we have p of x. Alright, so that's the universal quantifier. And then this one says there exists an x in the domain so that p of x. So this is talking about existence. This is the existential quantifier. And we're getting used to using these quantifiers. Example 1 here says let p of x say this. So p of x is giving us information about x. It's saying x is greater than or equal to 4. Q of x is saying something different. It says x is less than or equal to 10. Find the truth values of these statements. And the domain here is the set of integers. Okay, so part A, it's a simple one. For all x, p of x. Alright, so this is saying that every integer is greater than or equal to 4. It's saying every integer x has this property. Well, is that true? Can you think of a number that's not greater than or equal to 4? Yeah, so you can think of 3 or 2, or it has to be an integer, but negative 13, so any number to the left of 4 on the number line is going to work. As a counterexample, okay, so this is not true for every integer, so we say that this guy is false. P of x is true for some numbers like 4, 5, 6, but not for every number. Okay, so part A is false. Part B is saying there exists an x, there exists an integer, so that p of x and q of x, so we have a conjunction here. So is this true? So does there exist an integer that is greater than or equal to 4 and less than or equal to 10? Yeah, so that's true. You can find one. So any of the numbers 4, 5, 6, 7, 8, 9, or 10 are going to work. So this is true. Okay, a couple more. Part C, for all x, p of x or q of x. So for every integer, it's either greater than or equal to 4 or less than or equal to 10. Yeah, so that's true. Yeah, you could maybe look on the number line. So looking at all the integers, they're either greater than or equal to 4 or less than or equal to 10. So yeah, we're covering all the integers. So that's true. And last one, for all integers, p of x implies not q of x. So if the integer is greater than or equal to 4, that implies it is not less than or equal to 10. Okay, not less than or equal to 10, that's the same as saying greater than 10, strictly greater than. So is that true? If you have an integer that's greater than or equal to 4, that implies that it's strictly greater than 10. No, that's not true. The counterexample would be, say, 4 or 5. Alright, so you can see here we're combining these quantifiers with our usual logic operations and or implication, negation. And so yeah, so it's getting more complicated as we go. Translating from English to logic. Yeah, this can get tricky as well. Example 2, write this sentence using propositional functions and quantifiers. All monkeys can climb. Okay, so yeah, whenever you're dealing with quantifiers, yeah, first thing you should think of is what is the domain. And a simple way to do this question is to say the domain is just the set of monkeys. Okay, here's our propositional function. So c of x says that x can climb. And if we let the domain be the set of monkeys, then all monkeys can climb becomes, for all x, c of x. Okay, so the all here is referring to just the set of monkeys. Another way to do this question, yeah, if you let the domain be the set of all animals, and then to specify monkeys, let m of x say x is a monkey. Okay, so now the sentence becomes for all x, so for all animals now, if you're a monkey, that implies you can climb. Okay, so it's more complicated, but referring to all animals, yeah, we're only making a statement about monkeys. Okay, so if you're a dog, we're not saying anything. Okay, so but if you're a monkey, then you can climb. Okay, so why do we need an implication? Yeah, it's just because the sentence only refers to an animal if it's a monkey. Yeah, we couldn't use, let's say, an and here. So for all x, m of x, and c of x, so that's saying every animal is a monkey and it can climb. Yeah, that's not what we're saying. Not every animal is a monkey. Okay, another example, 3. Some monkeys cannot climb. Okay, so doing this the same way as the last example, this time the domain all animals. Okay, so some monkeys, yeah, we're not talking about all monkeys. So this is an existence statement. We could say it's the same as saying there exists an animal that is a monkey and cannot climb. Okay, so some monkeys cannot climb. So out of all the animals we're looking at, we want to say that there's a monkey that cannot climb. Okay, so we can write it like this. So yeah, we definitely need the existential quantifier. So there exists an x, there exists an animal that's a monkey and cannot climb. So the negation here. Okay, so instead of an if, we need an and in this situation. Okay, so and now we're talking about monkeys and they cannot climb. Okay, next, how about negating quantified expressions? So suppose you say all apples are red. So what's the negation of that? So again, negation means, yeah, we have this symbol and it means it's not the case that, in this case, all apples are red. Okay, so if it's not the case that all apples are red, yeah, what are you really saying? Well, it really means that there is an apple that is not red. Okay, so the kind of the opposite of saying all apples are red is saying there's an apple that's not red. Okay, so for negation of for all, you need there exists. So in logic here, let r of x say x is red, or domain is the set of all apples. Okay, so our original statement, all apples are red, looks like this for all x r of x. Here's the negation. So it's not the case that all apples are red is equivalent to there exists an apple that is not red. Alright, so the idea is if you want to negate a for all, you need a there exists. And this is related to De Morgan's laws, if you remember. So why is that? So let's say we just have three apples, A1, A2, A3. And then for all x, r of x is equivalent to saying r of A1 and r of A2 and r of A3. So we saw that before, so saying that all the apples are red, all these apples, is equivalent to saying the first is red, the second is red, and the third is red. So if you want to negate all the apples being red, that's the negation of these ands. And well, we saw it with 2, but it works with 3 or more. So De Morgan's law says if you want to negate something and something, it turns into an or. And so it's not r of A1 or not r of A2 or not r of A3. So if it's not the case that all the apples are red, that means either the first apple's not red, or the second apple's not red, or the third apple's not red. In other words, there exists an apple that is not red. Okay, so for all is uses the and operation. There exists uses the or operation. Alright, so this is the way to see that how the De Morgan's laws are related. And the other way around is the same. So if you're negating an existence, you need an universal quantifier for all. So if you say some bananas are green, then the negation of that, so if it's not the case that some bananas are green, that's the same as saying all bananas are not green. Okay, so here it is in the logic. So negating there exists a banana that's green is equivalent to saying all bananas are not green. Maybe they're all yellow. Okay, yeah, we're here. The domain is all the bananas, and g of x says x is green. Alright, so it's the same thing happening, that the quantifier switches and then the not moves inside. Okay, so here the negation is to the left of the quantifier, but to simplify it, we want the negation on the right side of the quantifier. Alright, so we get these, so they have the same name, so De Morgan's laws for quantifiers. So the negation of for all is equivalent to the existence with the negation on the inside, and the same thing for existence turns into a for all. So for simplifying these negations, we want to make sure that the negations are not to the left of the quantifiers. And so I hope it makes sense that, if it's not the case that we have p of x for all x, well, that's the same as saying, there exists, there must be some counterexample, there's some x where p of x is not true. And if it's not the case that there exists some x so that p of x, well, then it must always be the case that not p of x is true. Otherwise you'd have some example here. Okay, so an example of that, to find the negation of this expression and write your answer so that no negation is to the left of a quantifier. Alright, so here's the expression for all x, p of x, or q of x. Okay, so we can negate that. Just put a not outside with parentheses, and then hit it with De Morgan's first law here. Okay, so this is equivalent to there exists an x so that it's so that not p of x or q of x. Okay, so that's a good answer, but we can go one step further. Now apply one of the original De Morgan laws, so not p of x or q of x, that's equivalent to not p of x and not q of x. Alright, so maybe this is the best answer. Okay, so just to remember with De Morgan's laws, so for alls gets switched to there exists, and so ors gets switched to ands, and vice versa. Okay, one last example. Convert this sentence into logic, negate it, and write the negation in English. So this is the sentence. So there's a parrot that can count to 10. Right, so let the domain be all parrots, and t of x says x can count to 10. Right, so our original statement is there exists x, so that t of x, the negation of that, using De Morgan, that's for all x, not t of x. And in English, what does that say? It's saying all parrots cannot count to 10. Alright, so do you see that that's the negation of the original? Yeah, so you originally say, yeah, there is a parrot that can count to 10. If I contradict you and say, no, that's not true, then what I'm saying is all parrots cannot count to 10. Alright, so yeah, I hope that made sense.